We're going to be talking about impedance reflection in this video. It's a technique that allows you to easily calculate the input or the output impedance in transistor circuits. Let me show you what I mean. Imagine that we wanted to find the input impedance for this particular circuit. At first glance, we might just write that the input resistance is R1 in parallel with R2 because we have one branch going up here to an AC ground and we have another branch going down here. But what about the branch that goes into the base of the transistor? What's that resistance there? That's what we're going to talk about in this video. In the last video, I mentioned that there's a small resistance between the base and the emitter of a bipolar transistor. I'm going to go ahead and label that resistor little r sub e. We know that our impedance looking into the base of this transistor is somehow going to be related to the resistances connected to the emitter, little r sub e and big R sub e. But exactly how that's done is something I'm going to first show you and then explain why. In other words, I'm going to show you how to do impedance reflection. You look at a bipolar transistor and you see where the base is, and you imagine a wall separating the base side and the emitter side. If you see something on one side, you need to move it over to the other side. In this case, we have resistances over here at the emitter, and we need to move them over to the base. The technique for impedance reflection is to simply multiply those resistances times beta. If I were to go in the other direction to reflect impedances from the base to the emitter, I would divide by beta. In this case, I can improve my estimate for the input impedance by adding this new branch. I've multiplied my emitter resistances times beta and reflected them over to the base. This is how you do impedance reflection. Now I'm going to explain why we're able to do that. In order to answer this question, I'm going to draw the small signal AC equivalent circuit. What does the circuit look like, in other words, for the small signal that starts at the source and moves through the amplifier to the load? Well, let's start with the source. We then have the source resistance, which is the same. I'm going to skip the capacitor because if the capacitor is large enough or the source is at a high enough frequency, then it should just go right through that capacitor. Let's label Rn to be consistent with the circuit diagram on the left. Now from the perspective of the AC signal, resistor R1 leads to an AC ground up here at the top of the circuit. We then have resistor R2 leading to a real ground. We then have the base of our transistor, and I'm going to label it V sub B, and we're going to replace the transistor itself with a small signal model of the transistor. That is, over here we have a base, collector, and emitter, and I have the same 3 points over here. I'm now going to replace that transistor with something that does very similar things to what the transistor actually does. The transistor behaves a lot like a current source that multiplies the base current times beta and pulls it down through the collector. It doesn't matter what's connected up here to the collector, so I'm not going to draw it in my little circuit diagram here. I'm going to label R sub E, and now we're done with the AC equivalent circuit as far as the base side is concerned. I'm interested in knowing what the input impedance looking into the base is, so let me just label that R sub B. The equivalent resistance, R sub B, is just the voltage at the base divided by the current into the base. I can take note that the voltage here is just the base voltage, and I intend to apply Ohm's law across these two resistors. V equals IR, and I here is beta plus 1 times IB. I can plug the voltage into my equation for the resistance here. We can see in this equation that the I sub B cancels, and we're left with an expression for the resistance as seen from the base. I can go back to my original circuit diagram and say that my resistance as seen from the base is just by emitter resistors times beta plus 1. Now, I know I said earlier that all I needed to do was multiply it times beta, but beta is usually a pretty big number, so if you add 1 to beta, it's almost just like beta. Besides, the variation of beta from transistor to transistor is probably more than just 1. Therefore, this approximation is quite reasonable. Let's now work a few examples where we use impedance reflection. Let's find the input impedance to this example circuit. Let's first estimate it without using impedance reflection, and then let's refine our estimate by adding in the effect of the base resistance. By inspection, I can see that the input impedance should be something like 12 kiloohms in parallel with 8 kiloohms. If a transistor amplifier is well designed, it turns out that this is actually a reasonable approximation in most cases to the input impedance. This works out here to 4.8 kiloohms. Let's now include the effects of the emitter resistance in order to refine our estimate. Although I can probably ignore it here because it's going to be a small number relative to 1 kiloohm, I'm nonetheless going to find R sub E just to give ourselves some practice. We're going to need to know what the emitter current is in order to find that RE. First, let's find our base voltage, DC only. It's going to be a voltage divider set up by the two resistances, 12 kiloohms and 8 kiloohms. There's our power supply voltage at 10, and here's our voltage divider. We wind up with 4 volts at the base. Since our base emitter junction is basically a forward biased silicon diode, the emitter voltage should be around 0.7 volts below our base voltage. Our emitter current is just 3.3 volts divided by 1 kiloohm. We now have enough information to estimate little RE. At room temperature, we need to take 26 and divide it by our emitter current expressed in milliamps in order to estimate that resistance. Here it works out to 7.9 ohms. Let's now use it to find our input impedance. I again have the 12 kiloohm branch going up here to the AC ground. I then have the 8 kiloohm branch going down to the real ground. And I have one more branch going in here through the emitter. But using the techniques of impedance reflection, I need to multiply those resistances times beta because I'm moving them from emitter to base. We can estimate beta as being around 100, and we just calculated little r sub E. This resistance works out to be 101 kiloohms. That's pretty big relative to 12 and 8 kiloohms, so I'm guessing here that it's not going to make much of a difference. In fact, when you plug in the numbers, it works out to be 4.6 kiloohms. If we compare that to 4.8 kiloohms, we conclude that it might not have even been worth the effort to do all that work. It turns out that it makes more of a difference when you don't have a large emitter resistance connected down there to the transistor. Let's use impedance reflection again, but we're going to add this emitter bypass branch here to our circuit. Everything else here in our circuit was exactly the same as in the previous example. So I'm going to start off by just copying our calculation for the emitter resistance, little r sub E. As in the previous problem, it's 7.9 ohms. The DC bias points here are all the same, but I expect the AC gain of this circuit to be increased, of course, because of this extra branch. But here we're only interested in the input impedance. When I look in here to the amplifier, I see a 12 kiloohm resistor going upwards to an AC ground in parallel with an 8 kiloohm resistor going down here to a ground. And all that is in parallel to what we have going into the base of that transistor. Since it's on the right side of the wall instead of the left side, we're going to multiply all of those resistances times beta. Looking out of the emitter, we have R sub E, and then that's in series with two branches, each of them 1 kiloohm. We can again estimate beta as 100 and plug in our value for little r sub E here. In this example, the input impedance works out to be 4.4 kiloohms. In the last problem, it was 4.6 kiloohms. So what I can conclude here is that adding this branch to the circuit has reduced our input impedance a little bit. Let's work another problem where we get rid of this lower 1 kiloohm resistor completely and see what happens. The DC bias points in this circuit are again identical to those in the last two examples. So my little emitter resistance R sub E is again going to be the same number, 7.9 ohms. When calculating my emitter resistance, I have a 12 kiloohm branch looking upwards That's in parallel with an 8 kilo ohm branch going downwards. And then going into the base of that transistor, I see a 7.9 ohm resistor, and it's grounded directly through this capacitor. Applying impedance reflection, we only need to multiply it times beta. Beta times Re here is 790. That's substantially lower than both 12,000 and 8,000. So I can conclude here that the presence of this 10 nanofarad capacitor shunting my emitter resistance is going to have quite a large effect on my input impedance. When we plug in all the numbers, we get an input impedance here of 678 ohms. Comparing that to example 1, where we got 4.6 kilo ohms, we can see that this 10 nanofarad capacitor here, which we applied in order to increase the gain, has dropped our input impedance quite a bit. The second part of our problem here is to find the overall gain. In order to do that, let's draw a small signal equivalent circuit model for this particular amplifier. There we have our source and our input impedance. That takes care of the input side. Now let's draw the gain portion. The gain for a common emitter configuration circuit is the resistance connected to the collector divided by the resistance connected to the emitter. In this case, it's only little r sub b because it's shunted to ground through the 10 nanofarad capacitor. It's inverting because it's common emitter, but we can see that that ratio is going to be a fairly big number. We then have our output impedance, which is just 1.2 kilo ohms. It's a large resistance looking down the collector of a transistor, so I'm going to ignore it. And then finally we have our load. Let's now write an equation for the overall gain. I'll call this the input section. The input section creates a voltage divider. Now we have our gain section. And now we have our output voltage divider. Given how large our load resistor is here, I'm guessing that this ratio is going to be almost 1. When we plug in numbers for each of those sections, we find that the net gain is around negative 131. Now let's look back at what we've done, and let me ask a question. Where did we use impedance reflection in the calculation? Well, we only used it in one place. We used it when we calculated the input impedance, 678 ohms. I reflected what we see at the emitter over into the base side. However, when I calculated the emitter resistance in order to find the gain, I didn't reflect the impedances over from the base into the emitter, did I? I could have done that, but it's important not to use impedance reflection twice. Let me give you an alternative way of solving the problem, though, where we reflect the impedances in the other direction. An alternative way of finding the overall gain is to use the input divider without impedance reflection and then instead apply it to the gain segment. In other words, I'm going to assume that my input impedance doesn't include any impedance reflected from the emitter. Of course, that input impedance is wrong, but it's going to still give us the same and correct overall gain. Let me show you what I mean. Clearly, that's the wrong input divider, but I'm now going to compensate for it. Instead of just including my emitter resistance R sub E in my calculation for the gain, I'm now going to reflect in the other direction. I'm going to reflect the impedances seen looking back into the base onto my emitter side. When I do that, rather than multiplying times beta, I'm going to divide by beta. What do I see in this direction? Well, I see an 8 kilo ohm resistor in parallel with a 12 kilo ohm resistor in parallel with a 100 ohm resistor. Let me reflect that to my emitter side, and all that's in series with my little r sub e. The output segment here is unchanged from before. If we plug in values for beta and Re, identical to what we did earlier, we now have all of the numbers we need in order to calculate the gain using our alternative approach. It turns out that the answer is the same. So the point here is that if you're using impedance reflection in order to calculate something on your input segment, you shouldn't use it again for your gain segment. You should only use it once. Let me now show you why we can use impedance reflection going in the other direction, from base to emitter. We'll use that in order to calculate the output impedance here. First, I'll show you how it's done, and then I'll show you, using the small signal model, why we can do it. Looking to the left from the perspective of a small signal, I see my emitter resistance R sub E. I then have my little r sub e, and then I have to imagine that we have a wall, and anything on the other side of the wall can be reflected to my side of the wall only by dividing by beta. R2 is attached to ground. R1 is attached to an AC ground. For small signals, that capacitor doesn't exist. And then when we're calculating output impedance, we need to turn our sources off. So that's also attached to a ground. What do we have here? Well, we have RE in parallel with RE plus, because it's in series with 3 different branches here. That's our answer. That's how we can apply impedance reflection. But now let me prove to you that this expression is correct. I want to replace our circuit diagram and the transistor with a small signal equivalent model. To the left of the base, we have resistor R sub S, and we have 2 resistors in parallel with one another. We now reach the base of the transistor. AC base current little IB is going to flow into the base. We have some things connected to the collector, and I'm going to ignore them. What the transistor does is it creates a collector current by multiplying beta times the base current. There's our collector. We then have our emitter. And in this situation, I'm just going to draw the emitter resistance R sub E. I'm going to consider the resistance looking up this branch. Let's call this R out prime. Here it is on the original circuit, and here it is on our model. This is the answer we expect for R out prime. Let's see if we can come up with it. My technique is going to be replace everything to the left here by a Thevenin equivalent circuit. This is what I intend to do. In order to find the Thevenin equivalent circuit, I can imagine that everything to the right is disconnected, and then I just need to measure the voltage. It's just a voltage divider here. I can find my Thevenin equivalent resistance by zeroing out my source voltage. The resistors are all in parallel then. Let's draw the rest of my equivalent circuit over here. Output impedance is the open circuit voltage divided by the short circuit current. The open circuit voltage is easy because if I open it up right here, then no current is going to flow through that resistor. If no current is flowing through this resistor, then no current is going to flow through this branch or this branch, and I wind up with just our Thevenin voltage here. Let me now imagine what happens if I short it in order to find the short circuit current. I'll label this ISC. I'll label this I sub B. It's my base current. I now want to apply the Kirchhoff voltage law to this path in green. First we have a voltage rise, then we have a voltage fall, and then we have a voltage fall. Let me solve this equation for VTH. Let me now apply the Kirchhoff current law to this node. We have the base current coming in, we have the collector current coming in, and we have the short circuit current going out. The base current is thus the short circuit current divided by beta plus 1. I can now solve my VTH in terms of the short circuit current. We're going to use that short circuit current in order to calculate the output impedance. We're going to substitute this for VTH and then divide this by the short circuit current. The short circuit current just cancels from this expression. Let's make it disappear, and this gives us our final expression for the output impedance. We can see that this expression is actually equivalent to what we have here in the brackets. The only difference is that I used beta instead of beta plus 1. In any case, I hope that you're now convinced that impedance reflection works in both directions. Let's work another example. In this example, we're going to find the output impedance, and then we're going to calculate the overall voltage gain. As in the previous examples, the DC bias points are the same, so my emitter resistance, little re, is 7.9 ohms. Let's find our output impedance by applying impedance reflection. On the base side, we have 8 kiloohms in parallel with 100 ohms in parallel with 12 kiloohms. If I want to bring that to the right side of the wall, then I need to divide everything by beta. That's looking from the emitter into the base, so that's in series with my little r sub e. That's what we see looking up from this point. Since my R out is defined from the load resistor, then we have two branches. We have the branch going up here into the emitter, and then we have the other branch going down into the 1 kilo ohm resistor. We now have a full expression for my output impedance. That wasn't so hard, was it? You can almost do these things by inspection once you know the technique. If we plug in all the numbers, we find that the output impedance works out to about 8.7 ohms. That's nice and low. Remember, with a good amplifier, you should have a small output impedance. What kind of amplifier is this, by the way? Look, it's a common collector. Common collector amplifiers are known for having nice high input impedances and nice low output impedances. The gain, on the other hand, is usually about 1. These kinds of amplifiers make good buffers. Let's now draw an equivalent circuit model in order to find an overall expression for the voltage gain. Remember, we should normally only apply impedance reflection once so that we don't wind up double counting things. In this case, I'm only going to use impedance reflection for the output portion of the circuit, not for the input portion. It means that my input impedance is going to be inaccurate if I focus on that section alone. That is to say, since I'm using impedance reflection on the output side of the circuit, everything's going to work, but this is not going to be the real base voltage. The gain section for a common collector amplifier is just 1. Now for my voltage divider, I have normally my emitter resistance, my 1 kilo ohm emitter resistance. For my output section, I have my emitter resistance little r sub e, the large resistor 1 kilo ohm, and then my load of 200 ohms. However, I'm going to use impedance reflection to refine my value of r sub e. I'll call this r sub b, and here's what I'm talking about. It's my resistances at the base that have been reflected over to the emitter side. If I find the output voltage here, then I'll have an accurate expression for the voltage gain. Let's go ahead and do it. This represents the voltage divider from my input section. Now we have our gain section, which is just 1 for a common collector amplifier. We now have an output section. It's just a voltage divider across these two resistors. When we plug in numbers here and divide everything by beta, it turns out to be a really low number, about 1 ohm. In other words, it's not going to matter very much. The overall gain here works out to be 0.93. You might be a little bit confused about me not using impedance reflection for the input side. I used it for the output side instead. Let me now show you an alternative way of finding the gain where we reflect the emitter resistance over to the base side. In this method, I'm going to bring the resistors that are connected to the emitter over here to the base. I'll have to multiply them by beta in order to do that. Let's draw the equivalent circuit. Now I'm going to apply impedance reflection. What do I see at the emitter side? Well, I have the emitter resistance plus 1K in parallel with my 200 ohm load. That's all going to have to be multiplied times beta in order to properly reflect it into the base. That's our input side. Now we have our gain section. For a common collector amplifier, it's just 1. However, now when I continue working on my output section, I shouldn't apply impedance reflection again. That would somehow double count the resistances. This is just going to be little r sub e. Overall, I like this method a little bit better because it gives you an accurate voltage at the base. The input impedance is also accurate. However, when you actually calculate the output impedance, you have to reflect the base impedances over to the emitter side. Let's now calculate the gain using this alternative method. From the input side, we have a voltage divider. When we apply the numbers, it works out to 0.97. Impedance reflection didn't make much of a difference here. Our gain section is just 1, and then our output impedance gives us a voltage divider here as well. It works out to 0.96. It comes out, when we multiply these things together, to 0.93. It's exactly what we got before, and it turns out that the two methods are entirely equivalent to one another. In the next video, we're going to work a few example problems, specifically with the common emitter configuration. Let's apply what we just learned to some examples.